Welcome, everybody. I think we'll get started now. I'm Jerry Schmall from the University of Iowa, and Victor and Susan asked me to help lead this session in Legends of Environmental Chemistry, Take 2. This is our second of 4 sessions. Our first talk today is by our legend, Fred McLafferty. Fred's from Cornell University. He's going to speak to us on early environmental chemistry, both industrial and academic. He is known to many of you and was mentioned several times by our speakers this morning for his pioneering efforts in environmental movement, especially with respect to identifying unknown pollutants in environmental samples. His books are still widely used in academia today, I can tell you, on mass spectra. His top-down proteomics techniques for MS characterization of proteins, which combine Fourier transform mass spectrometry with electrospray ionization, and it now includes electron capture dissociation to provide far higher specificity for localization of post-translational modifications. So he's really a member of the omics revolution in using environmental analytical techniques to help understand proteomics. His most recent extension is a top-down technique to take us from 50 kilodalton proteins up to 200 kilodalton proteins and beyond, including gas phase protein ion conformations.
There is no
Fred's database includes 600,000 electron ionization mass spectra, which I hope will tell us not about all 600,000, but a little bit about how we came to this place today. It's my great pleasure to introduce to you our legend, Fred McLafferty.
Thank you, Jerry. Thank you. Thank you. Thank you. I hope you weren't watching the slides because I did this first slide especially for Susan, my good friend Susan. At least up till now has been my good friend. Susan saw me at a meeting and she said, Fred, I've heard lots and lots and lots of your talks, and your talks are just perfect for this symposium about legends. And so I looked up legends, and I know she knew me very well. So anyway, I'll give you my usual kind of talk in which we'll give you lots of legends about things. We hope this will work. And we'll start off
It's not plugged in. We don't have the sender plugged in.
Oh. Details. Perfect. We'll start off. I was not a student of J.J. Thompson's, but since this is environmental, this is Thompson invented the mass spectrometer, and this is one of his first mass spectra. Back in those days, mass spectra looked a little different than they do now, but this was a marvelous scientific discovery in that you may remember in those days they were measuring atomic weights, and carbon was 12, almost exactly 12, and nitrogen almost exactly 14, and oxygen almost exactly 16, but they got up to neon, and neon was 20.2, and they analyzed it and analyzed it and analyzed it, and it still stayed 20.2, and here is the mass spectrum by J.J. Thompson. There's neon 20 right here and neon 22 right here, and the relative abundance of 22 was 10%, which of course made the 20.2 work out very beautifully. But I like this because you can see that environmental things were there already. Carbon dioxide, carbon monoxide, you can see he was finding, And mercury, of course, he used a mercury diffusion pump, but still you can see he got both the singly and doubly charged mercury peaks in there. And in his first book on mass spectrometry, he put in that this method should be very good for analyzing things, and he even included molecules. Well, for many years, the molecules weren't very important for mass spectrometry, partly because they used electric discharge ionization. They just put things into an electric discharge, which kind of tore molecules apart. Here's his student Aston, who also got the Nobel Prize, only he got it for mass spectrometry. And you can see the kinds of things he ran in his much better instrument that used photographic plates, but he did have molecules like SO2, and here's the 76 molecular ion of SO2, and he even had methyl bromide, which has the 79 and 81 isotopes of bromine very clearly, but if you look up in here for methyl bromide molecular ions, there's not much there after the electric discharge ionization. Now, I forgot, this is one of the things he says for you mass spectrometrists present that has always been true for us. The mass spectrometer has an extraordinary power of resurrecting the spectra of gases previously used in the apparatus, which is, of course is called background, and it's a wonderful instrument for seeing things that you didn't put in there but somebody else did. But for environmental samples, Bill Buddy's already told you enough about that kind of thing, so at least Aston was ahead of the rest of us on that kind of a thing. Now, since I'm at Cornell, I like to cite one of the first publications about molecules in the mass spectrometer. I like to call it molecular mass spectrometry. And this was, he ran benzene and carbon bisulfide, very large molecules. And he told us, for example, that when you run large molecules in a mass spectrograph, you have to make special cautionary things, and you have to have high resolving power for your large molecules. Now, Bill Buddy already told you about electrospray ionization, but this was slightly before that, and I've always loved this kind of precautionary thing. And so, however, he used what we call electron ionization mass spectrometry, which isn't as rough on things. And you can see that here's his mass spectrum of benzene. There's a nice, great big molecular ion now for benzene. And as far as resolution is concerned, he has at least 78 resolving power, because the 77 C6H5 peak is resolved. And so in 1932, that's pretty great stuff. My next Cornell connection on mass spectrometry is Simon Bauer, who joined the Cornell chemistry faculty in 1937, and this is his PhD thesis at the University of Chicago. And he worked for Professor Hogness, and Hogness said, well, for what we're going to do, we need a mass spectrometer, so you have to build a mass spectrometer for your PhD thesis. And you may remember that the first commercially successful mass spectrometer, and it was really very successful, was the Consolidated Electrodynamics Corporation 21-102 and 103 instrument, and it was based on the Dempster 180-degree geometry, and Dempster was at the University of Chicago. And so Bauer loves to tell the story that he, of course, when he went to Professor Dempster, and he said that he says, I have to build a mass spectrometer for my PhD thesis. And Dempster said, when I was a grad student, the professor did not have to do the literature search for a graduate student. End of story. And so he loves to tell that story to this day because Professor Bauer at 95 is still writing papers. But so I'm glad to be here as a young person in one of the younger persons in mass spectrometry. Anyway, you can see that methyl chloride, and these are galvanometer measurements, a peak at a time, and this is voltage going this way, so of course the mass goes the other way. So where do I enter the story? Well, I entered the story in as far as mass spectrometry is concerned when I went to the Dow Chemical Company in 1950. I didn't learn mass spectrometry when I was a grad student at Cornell from 1947 to 49. And I actually did a postdoctorate at a very highly honorable institution, ask Jerry, the University of Iowa, where I worked for Ralph Schreiner, who authored many, many editions of Schreiner and Fuson, which was the way to do qualitative analysis of organic compounds. Only used entirely organic chemistry to do this. I had never seen a mass spectrometer. And so after I looked for an academic job unsuccessfully, I went to the ACS meeting, of course. I interviewed at the industrial and everything places. I got invited to the Dow Chemical Company as an organic chemist. I had actually got my PhD in organofluorine chemistry. And when I got there in the morning, they said, oh, you're going to interview at the organic lab this afternoon, but the spectroscopy lab needs an organic chemist, and so you're going there for the morning. I said, what for? Oh, for the mass spectrometer. And I said, I've never seen a mass spectrometer. Oh, that doesn't matter. I've been told it really doesn't matter. And so when I got to the mass spectrometry laboratory, there's Vic Caldecourt. And Vic was Mr. Mass Spectrometry, only he really loved the instrument much more than running samples. And Vic said, well, this thing is really very simple, and that mass spectrometer happened to be running butane at the time. He says, look, the butane is C4H10, therefore there's a peak of 58, and it loses a methyl group. That's a propyl, that's C3H7, that's a 43 peak, and so there's got to be a 29 and a 15. It's really all very simple. It's the kind of thing that I always put to loosen up foreign audiences that haven't heard of the mass spectrometer, that the mass spectrometer is indeed very simple, and you can even use these peaks to tell the difference, to do structure determination, because you can tell it's HOH and not HHO because there's no peak at mass 2. So you can see here was all there is to mass spectrometry in a 10-minute lesson from Vic Caldecourt, and I haven't learned much since, but anyway, this is the great way I got started in mass spectrometry. So what did we do back in those days? Well, we had a Westinghouse 90-degree sector instrument. When I went to Pittsburgh conference, almost everybody there was in the petroleum industry. Almost everybody had a CEC 21103. But Vic, the kind of guy that he needed another mass spectrometer, and Westinghouse was just going out of the business. They got out-competed by this Dempster instrument, and so Vic was building a second mass spectrometer, which was just fine. And so by far the most important thing that got me going in my career was that I didn't have to worry about the mass spectrometer. Vic was one of those guys that could always put his hand on the relay rack and tell you to replace that tube or something like that. And he did all sorts of things. For example, we could scan a spectrum in 30 minutes. We could run 8 or 10 samples a day, and we ran 2 shifts, And of course, we then had 4 mass spectrometers, and the hourly people ran the mass spectrometers. The sensitivity really amazed me because the strip chart recorder would go right off the top of the chart with the kinds of ion currents that we had. And so Vic built 2 automatic range changers that as soon as it started up, and it was going too fast, it would switch over by an order of magnitude. If it's still going too fast, another order of magnitude. So on this 30-minute spectrum, you could see by the way the thing jumped that that this peak was, you had to divide by 100 in order to get the height of this peak. No instruments in those days had mass markers. Well, you saw things in Bill Buddy's talk about that. Vic built a mass marker that was a vibrating coil that was down in the magnetic field. So it sensed the magnetic field. He took the output from this coil and he ran a little motor, and this motor ran between 2 reels an exposed movie film. But exposed movie film, it was rough enough you could write on it with a pencil, and so the operator, as the thing is scanning, if they see the peaks of water go by, and they know they are, they draw a line on there and write 18 down. Or if it's butane, a line and it's 58. And so we had a mass marker, and the operator had to put the masses on the strip chart recorder. And so Vic was absolutely marvelous for all this. Samples, one of the big things was to have a heated inlet system so you could run less volatile samples. Vic invented a thing where you weighed your sample in a little Teflon cup, put it on the top of this 5-liter sphere, and the hole was already sealed with another Teflon slug. You put another one on top of it, you pulled this handle and popped both things in and left one in the top, and that way you could run weighed samples. So, well, Vic was terrific. And so one of the first things I could find that I'd published was the Pittsburgh Analytical Conference of March 2 to 6, 1953. Now, my family always remembers this conference and gives me a hard time because I did arrive home in the evening of March 6, 1953, and our second child, Joel, was born on March 6, 1953, and my neighbor got me to the hospital a whole hour ahead of time. So my family still remembers that I love analytical chemistry that much. And my wife's forgiven me after just 60 years of marriage. And anyway, this abstract says small sample requirement, sensitivity, speed. We've been talking about the same thing in mass spec ever since. Routine survey of industrial plant areas for possible atmospheric hazards. Well, that has a story too. How's my storyline going? I still have a few minutes. Anyway, in Midland, Michigan, had about 20,000 residents at the time. 12,000 of them worked for the Dow Chemical Company in Midland, Michigan. And the styrene plant inside the fence line was about 2 blocks from the bromine plant. Whenever they were making things vigorously so that there's some effluence coming out of the plant, and the wind was in the right direction, so it took the vapors from one to the other, people downwind cried. Tears ran out in the parking lot. I can remember everybody in the parking lot had tears running down their cheeks like this. And the reason I got into this marvelous research on atmospheric pollutants was I was supposed to catch this wonderful lacrimator and find out what it was. And it turned out to be the bromohydrin of styrene. And unfortunately, the infrared lab identified it, and I didn't. Mass spectrometer didn't. Well, it doesn't give a molecular ion, and anyway, and this was. I also knew Detroit was having a terrible time with air pollution, and I got acquainted with some of the people down there in the air pollution business, and they said, you can identify things? Oh, when we have an inversion, I think you remember inversions from LA and everything. When we have an inversion, we have all sorts of problems with people coughing. Come down and sample our inversion. So Roland Golke and I got our apparatus of collecting with liquid nitrogen and passing air through it, and we had a pump and everything, and put it in the back of my car, and we drove down there, and I asked the guy, how do you tell an inversion? Oh, you'll know it. It just changes everything, and blah, 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 blah. And we sat in the outskirts of Detroit until about 5 a.m., and we sampled every once in a while, but then we drove home in disgust, and the guy says, oh, it just didn't happen this time. Well, anyway, that was enough for my adventures in atmospheric pollutants, and there might have been another reason. I discovered in a lab notebook that in trying to be quantitative about this, the best recovery I ever found with the apparatus I had was 19.4%. You know, 3 significant figures, but still maybe not perfect. I found this slide about atmospheric analysis, and I thought it's at least, though it's 1976, at least it's a good one to give credit to Klaus Beeman, who did the lander program and found no life on Mars. He's at a time from Gaumac, they made special detectors for him because they hadn't had orders like this in quite a while. He built something like 200 of these instruments for various plants and labs all over Dow, Texas, Dow, California, everything else, before commercial GCs people would even look at them. And so this was great fun that Roland, he had he put everything in a 5-liter dewar, so he could thermostat the whole thing with a heater in there, put everything in a 5-liter dewar, so his package was just a 5-liter dewar they could put out in the plant. And then we had these friends at the Pittsburgh conference. I had gotten acquainted with Bill Wiley at Bendix, and actually the Bendix Research Lab was in North Detroit, so they weren't very far from us. Ian McLaren is the one that worked with Wiley to develop the instrument. Dan Harrington was a young guy just in the lab, but he represented Bendix instrument sales for many, many years, and Dan was a great guy. And so one day in the winter of 1956, we put Roland's GC and stuff in the back seat of the car, and we drove down here to hook it on to the Bendix time-of-flight instrument. Well, I asked them if they had any organic chemicals we could just try it out before we tried Roland's. Roland brought some samples along, and they said, we've never had any organic compounds in this instrument before, and they were rather suspicious of trying this, but they were good sorts, and they tried it. And so here's the time-of-flight instrument, of course, did 10,000 spectra per second. You didn't have to worry about getting a whole spectrum while the peak came out of your GC. And you would just see these rise up on the oscilloscope and rise back down. And they had 2 oscilloscopes, one with the Polaroid camera on it to take these pictures. And Roland sat there telling them when to push the button on the Polaroid camera, and the rest of us had to look at things. But Dan Harrington always reminded me that I'm supposed to be the guy that could interpret mass spectra, but as these things come flashing up on the screen, Roland would say, acetone. And then I'd say, oh, yeah, acetone. And then benzene. And years went by, and I'd always get teased about the fact that Golke could do this faster. I finally realized that Golke was the guy that made up these samples ahead of time. He was the guy that tried it on the same gas chromatograph with an ordinary detector before we went down there. And he never once told me. And all those years, I got teased about it. But anyway, we'll give Roland credit for this. Here's another thing. Of course, one thing that slowed GC mass spec down was the separator, because you put all this helium in the mass spectrometer along. And how to use separators? I want to show you the very first real separator that really worked, and it's never been published. And I've shown this same slide that I did by hand 30, 40 years ago. But Roland deserves all the credit for this, but let me show you in case you haven't seen it. This is the Golke separator. He has the Bendix time of flight. Thank you. I'm glad to hear you're so interested. You see his finger here on the inlet side of the mass spectrometer. There was a petcock where we pumped down the instrument before we really turned on the diffusion pumps. And so Roland puts his finger on this petcock and opens the valve, so he's pulling a vacuum on his finger. And of course the oscilloscope is just showing water and air and that stuff. And this is at a demonstration of an open house. I wasn't in the lab at the time. He did this all by himself. I happened to be back there because in 1956 I went back to the Boston area to set up a basic research lab for Dow. Anyway, within about 25 seconds, up on the oscilloscope goes the mass spectrum of carbon tetrachloride. Great separator. He demonstrated then what happens with other things. For example, when he used dimethyl sulfoxide, if you know it goes how fast it goes through this, he didn't get a spectrum. He shut down the whole vacuum system because so much gas came into the mass spectrometer. So in case you want to try this out, you might try it with ethanol instead of carbon tetrachloride. But in fact, Roland's gone now. He died of cancer half a dozen years ago. So maybe this experiment is what did him in. But certainly back in those days when you got tar on your hands at the Dow Chemical Company, you washed it off with carbon tetrachloride, Dow carbon tetrachloride. So anyway, Roland never got credit for this great separator. So let's talk a little more about identifying molecules in the mass spectrometer, because it's kind of like Bill Buddy's talk that they went through a period of trying to get the GC mass spec as the method of analysis for environmental problems. We had a terrible time back then convincing anybody that the mass spectrometer could tell you anything about the structure of the molecule. And of course, the biggest problem there was 95% of mass spectrometry was in the petroleum industry, and so involved hydrocarbons. And a hydrocarbon mass spectrum, the theory of the general theory of fragmentation back in those days, at least by my friends who wanted to make fun of mass spectrometry, was the canvas bag theory. You took the molecule, you put it in a canvas bag, the same one you use for dry ice, and then you pound it with a hammer, and then you dump out the pieces, and those are the kind of pieces you get in the mass spectrometer. And so this is one of the John Bynum was a pioneer, and these are my notes from the 1955 mass spectrometry meeting in San Francisco. And John Bynum had a high-resolution mass spectrometer. He actually visited my lab in Midland, Michigan at the same time. And he showed that the molecular ion, he not only could get its mass, he could get its elemental composition by measuring it as accurately. And he could show that it was C3H5 loss from it, and a C4H6 loss, and a C4H7O. He could tell the difference between O and CH4, and that there was a C6H5 peak. And if you put all of these together, as he showed, you can get this molecule that's the butynyl ester, 1-butene ester of benzoic acid. And actually, he tried to get me at Dow to buy one of these high-resolution instruments at the time, because if we bought two, we could get them cheaper, and I wasn't smart enough to even do this. But anyway, this, and John, of course, book in 1960 was a tremendous help for getting things going. Here's one of the most exciting things for getting structure determination going, and Ragnar Rihage and Einar Stenhagen, both good friends of mine, and in 1958 we happened to visit Stockholm, and I was shown this spectrum. They ran it on 1 microgram, molecular weight 494, and it just blew me away for what we could do at that time. We hardly ever ran anything except halogenated things bigger than 150. And you can see, well, I even show this now for top-down proteomics, because this was nothing new about top-down. Well, I think I even have some. If you lose 28, there's a methyl group attached. If you lose 14, there's no methyl group attached. And you can see all these things. And in fact, those first things, there are rearrangements. My rearrangement paper got published in 1956. And so these kinds of things were beginning to at least take hold in those days. Klaus Beeman, I gave some credit to before. Klaus, of course, was a tremendous factor in making all this go. And then there were some real nifty publications that attracted real organic chemists in those days. Barry Trost was a real organic chemist at the University of Wisconsin. Chuck Sweeley at Michigan State collaborated with him here. John Law at the University of Chicago, this juvenile hormone was a very famous case of identification. I've forgotten, 10 molecules of it will make the male moth attracted from a zillion miles away or something like that. And of course, molecular weights were a terrible problem, and by permethylating some peptides, Mickey Barber, who started his career in Edgar Lederer's lab at GIF just outside of Paris, really got the protein chemists excited early on with this kind of a thing. And so I want to spend my last few minutes talking about mass spectrometry identifying molecules. And the first thing that is hard to get across to people is that, I have a story, infrared NMR mass spec. I forgot a story that I wanted to tell you about the 1959 Pittsburgh Analytical Conference. And Don Cook, who's a Cornell professor of analytical chemistry, who's just died this last fall, and my longtime friend, arranged a symposium to compare these new methods of identifying molecules. And he invited Jim Schulery from Varian for NMR, and Bill Potts. I told you Dow had a great infrared lab. Bill Potts from Dow, and we're all experts in our own field. And what he did was he had three projectors set up, and a big and screens for all of these. And at the same instant, he would have all three projectors shifted so that one, for a particular compound, one would show the infrared spectrum, one would show the NMR spectrum, and one would show the mass spectrum. And then we had a race to see, without reference or anything else, who could identify it first. And for years after that, well, when I went to Cornell in 1968, Don was teaching this interpretation course, and so he said, well, and so I got to teach the mass spec part of it with him. We shared the course then for a while. And he would always start off the course telling this story to all of the students, that what you really need to do is know this well enough so that you could compete in this kind of environment. And his favorite one was that all three went up, and within a heartbeat I said nicotine, and these other two guys, everybody was laughing so that the other two guys finally didn't even try, and they cried foul, and Don's my friend, and he must have set me up and so forth. And so Don asked me, and I said, oh, I just remember the spectrum of nicotine. And I'm not a smoker either. So ever since then, he's used this story. And so having looked at quite a few spectra, like Bill Buddy has, helps you in interpreting spectra. But anyway, now that I've told you that, let me give you the full story. The reason mass spec is the role mass spec has in this is for the global unknown. That is, if you haven't any idea what it is, it's way out there someplace. Mass spec is much better at focusing you in on something. The reason the organic chemists love IR and especially NMR is they already know an awful lot about the thing, and they want a particular answer, and so it's great for that. And of course that means that all three methods are fine, they're complementary, but as far as having a global unknown where Chemical Abstracts has listed already more molecules than I can remember, and your body can make up to 10 to the 9th immunoglobulins. There are so many possible things that maybe we need help in this sort of thing. And so here's an example I love, because Klaus Keppel was a postdoc with me. He did his PhD with Helmut Schwartz in Berlin. He was so impressed with the research in my lab that he went back to Berlin and got his MD. But he did then use his mass spec because he was in charge of the emergency room in the Charlottenburg Hospital, which served all of West Berlin, several million people in those days. He told the story of an unconscious man came into the emergency room. They ran GC mass spec on him, and they got this very unusual mass spectrum at the top. And for you mass spectrometrists in the crowd, you'll notice that it has a nice, great big molecular ion, so it's a very stable molecule and so forth, but it has this strange array of 5 peaks, all separated by 16 mass units. Of course, oxygen should be 16, so how is this? Well, of course, I was stuck. And but of course, if you then search the database, and luckily this was in the database in those days, it's DAP zone. And you can see the SO2 in the middle. When two aromatic rings are close to each other, they like to get together and spit out the pieces in between, and they spit out the oxygens and sulfurs so that you got 5 separate peaks. But the other part of the story that was kind of fascinating is, if you look down here, this is the Merck index. The main therapeutical use for this is as a leprostatic. It's a leprosy drug. And Keppel said the other doctors in attendance said, you're out of your cotton picking mind. There hasn't been a case of leprosy in Berlin since 1307 or something like that. And so they looked at, well, this lists the toxic action, all these things. It's a beta blocker, and so they treated the patient for how you treat for beta blockers, and he survived. And so when he could talk, they said, well, where did you get Dapsone. He says, oh, I have no idea what I took, but I was feeling suicidal, something about his girlfriend. No, it couldn't be that. Had to be something more serious. Anyway, he said, and I work in the main warehouse of XYZ pharmaceutical companies, so I just walked into the stockroom. I picked the first thing off the shelf, didn't look at it, and just swigged it down, and that's how I got it. So anyway, I was told I could tell stories. Wind it up. Almost done. And so we devised long ago a punch card filing system for going through these things, and we did publish that. And we have now databases. We're finally bringing out a 9th edition of the Wiley Registry. It takes us less than a second to search this with the probability-based matching system. And I just wanted, in the last couple of seconds, I'd like to show you the common thing that people do wrong compared to other common systems. Our PBM system is about the same in the #1 rank, but it's not. This is a terrible mistake, because that means the people that don't know much about mass spec just look and see which is the closest matching spectrum, and they say that's the correct answer. And of course, if the compound's not in the database, then you got the wrong answer. And so this reliability recall plot that you see here is what will tell you what the probability that you have the right answer, and the probability is never over 99%. And so you can see that having the probability-based matching does a far better job. And this is also a reverse search system, and so the great advantage there is that if there are 2 of the same compounds in this one GC peak, it finds them because it doesn't demand, it only looks to see if the peaks of the reference compound happen to be in the unknown and not vice versa. And so in this case, it got both of these. And for this kind of thing, you can see that the PBM works far, far better than the other kinds of systems. And so mass spectrometry today is using all of these. I'd like to end up with this. I've shown this before, but my great good friend, Professor Julie Leary, when we had the 50th anniversary meeting, she was then at Berkeley, she's now at Davis, but anyway, she wrote me and said, for our 50th anniversary ASMS meeting, we would like to exhibit interesting mass spectrometry artifacts. And so I come here as both a legend and an artifact. Thank you very much.